you have one object traveling at two different speeds in two different mediums. Might behave the same way, and then if you read Feynman's book, QED, he talks about it still works even when you're dealing with quantum physics. Questions? All right, so as mentioned before, this works for any type of wave, sound or light. But let's see if it works all the time. If I know what's good for one, do I know what's good for the other? The answer is, of course, no. If I'm dealing with a wave, we'll just take the simple case of I have a wave propagating along a string. I know that if we analyze that point right there, we saw that the force acting on that point was proportional to the acceleration. If you went back and looked at the derivation, we had this relationship. More specifically, the force was proportional to, well, the force equal K Y, that's equal to the mass times acceleration, negative. Because the displacement Y is up and the acceleration is down when we're at the peak. So we can make the assumption, and we only look at it for one point, but let's go ahead and assume that it is true for every point, all along the point as it moves up, or at least close enough. Since it obeys Hooke's law, I can look at the energy as 1/2 K Y squared. I know that K is equal to omega squared M, so I can substitute that into there. So the energy, crudely, is M omega squared Y squared. Now, we're only looking at the small segment of mass here, not the whole thing, and so we really should be talking in terms of differentials. 1/2 omega squared Y squared dm. Which, if we bring in this idea of a uniform linear density, that's mass over length, or if it's uniform, that should be equal to dm dl. If we take some small segment, this was a substitution that we had made when we were dealing with it earlier. So this becomes 1/2 omega squared Y squared mu dl. Now, if I take the derivative with respect to time, or divide by dt, so dE dt, it's the rate at which the energy is being given or used, depending upon how you want to look at it. That's equal to 1/2 omega squared Y squared mu dl dt. And what is dl dt? Think of dl as being the segment, say, along here at that length. think of it simply. What is DL? What would the units of DL be? Okay, it's a length divided by a time.
A speed?
It is. So it's 1/2 omega squared times y, which I'm gonna go ahead and just look at the amplitude, u times v. And this energy with respect to time, the rate at which energy is being used, we didn't really talk about that, but do you happen to know what it is? I would take that as a no. That's power. So the power that is being exerted is how much energy is being used with respect to time, or how much work is being done with respect to time. So I have an equation here for the power in a wave. Now, or I can look at it from an energy point of view a little bit more macroscopically. So, these are equations for waves. Let's think about the implication of it. It's going to bleed a little bit into 252, but it's just sort of a sneak preview, I guess. If I take a surface here, some metal, usually it's a metal, and I shine light onto it. That if I shine light onto it, that it is possible to have an electron be kicked off, that there's enough energy in the wave that it's going to kick this electron off. Now there's a threshold. There's at some point where there's not enough energy to kick the electron out. This is known as the photoelectric effect. So if light is a wave, then if this is the amount of energy in the wave or the amount of power produced by the wave, I should be able to eject the electrons. If the light's not enough to eject it, I should just be able to crank up the amplitude, make it brighter. Higher amplitude of light, brighter light. And it turns out that doesn't work. If the light is not enough to kick the electron out, turning up the amplitude does not help it. That what really matters is the frequency of the wave, not the amplitude of the wave. So if light does not obey these rules from waves, is light a wave? Well, it obeys Snell's law, that's a wave thing. There's all sorts of things that light obeys if it's a wave, but not everything. Sometimes it doesn't behave like a wave. And so this is one of those things that was sort of perplexing physicists about 100 or so years ago. And then they came up with this duality thing that sometimes light behaves like a particle, sometimes it behaves like a wave, otherwise known as wave-particle duality. There was one term, never really caught on, called a wavicle, but it seems like, yeah, I feel like wavicle works, but no one else does. So Newton was a big advocate of the particle theory. Huygens, who was his arch nemesis in some respect, said it was a wave. There was a famous experiment where it does behave like a wave. If I have a barrier here with two gaps in it, and I send light towards it, if light is a particle, you would expect particles to hit here, and what I would see would be a big spike there and a big spike there, if wave's a particle. If light's a particle. If light is a wave, what I would expect to see when it hits that barrier, well, think about water. If water is coming in like this, it's going to hit this, and then it's going to start rippling. These are peaks here, so what I would expect is there'd be points where they overlap, constructive interference, so I'd get a bright spot, and parts where one's peaking and one's bottoming out, troughing, in which case I'd get a dark spot. And so in this case, what you would see is a bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. And this is what you see. Except, if we put a monitor here, so we know which, so we could actually test to see this thing coming through it. We get that. But just a sneak preview of 252. Oh, before I erase more.
So is it just light that varies energy with frequency?
Just recognize that the term light is a very broad term in physics, that it's not just visible light, but it's microwaves and ultra high frequencies.
Electromagnetic radiation?
Yeah, electromagnetic radiation.
But other waves, the energy is related to the amplitude.
Yeah.
So sound, for example.
Yes, sound definitely is a wave. It's conducted by particles, but it is a wave. You would not confuse sound. You could not model sound, think of it as a single particle. Not easily, at least. I guess there's what one professor called conservation of complexity. So if I treat it like a particle, there's just a bunch of stuff in there. Other questions? All right, let's talk about the next quizzes and tests. So that was chapters 16, 17, and 18. All right. Definitely not gonna make it do the 27th or the 20th. I'm thinking the 30th for the master set. Is that, I don't know what your Thanksgiving plans are. If you feel like your Thanksgiving plans would not work with that, we can push it off till the following Tuesday.
Should work for me.
That works for you?
Yeah.
All right. And then the quiz. Calendar. Wrong one. All right, so the 4th, December. December 4th, the quiz 16 through 18. That's master set. All right. Any comments or counter proposals? All right, the thermodynamics section. I'm not going to go in the same sequential order that the book does. Just because. Similar to 16 through 18, I think I kind of went along with it, but not 100%. is look at particles in a box. So I have particles in a box that are going in all sorts of directions. We assume that there's a random number of, that they're randomly distributed throughout there, or it should even say evenly distributed throughout and going in random directions at various speeds. When a particle hits a wall, we're going to assume perfect walls that the particle is going to hit it and bounce back. So the particle will bounce off walls with no loss of energy. So perfectly elastic collision. So as the item, as it hits at some, we'll just say for straight on for right now, we have some particle of mass m, this is a wall, traveling at some velocity v. It's going to hit the wall, bounce back, so we'll have this mass m traveling with a velocity of negative v. Let's narrow it down. We'll just look at the x component. So the impulse on the wall should be equal to the negative impulse on the particle. If momentum is conserved, for perfectly elastic collision there, the change in momentum of the wall should be equal to the negative change in momentum of the particle. So this is negative I particle final minus I particle initial, which is negative mvx plus minus mvx, which is 2mvx. That is the impulse exerted on the wall. Now we know that if I got a box with a bunch of particles in it, more than one particle is going to hit it, and so let's sort of expand that. There it is. So if there are n particles, let's see if I'm trying to keep the same notes there. So we have n call, which is the number of particles hitting the wall. And obviously we should put a time limit on there. So what I'm going to look at here is, well, I know the impulse from one of them is 2mvx. This is for one. If I have n particles, then 2nmvx. If I want to look at it with respect to time, so the number of particles that hit within a certain amount of time, that's 2, oh, that should be n call. N call over time, mvx. I'll make that differential at this point. So let's think about what this means, first off. What is impulse?
Change in momentum.
Yeah. So impulse equals change in momentum. And what is momentum?
Mass times velocity.
If we assume that the mass is not changing, that the particle is going to hit the wall and bounce back, and the mass doesn't, so it doesn't burst into flames or anything like that. We have, this is equal to mass times the change in velocity is equal to impulse. And again, making the assumption the mass isn't changing. If I divide by time, those are vectors. What's the change in velocity over change in time?
Acceleration.
So my impulse divided by time is just the force. Matter of fact, specifically in this case, it's the force in the x direction. All right, let's see if we can come up with an estimate for n call, the number of particles that will collide in a certain amount of time. If we think about it, if I have a very short amount of time, the only particles that are going to hit, let's just say this wall right here, and this does not work on the board. The number of particles that are going to hit this are only those that are within a certain amount of distance from it. And the number of particles in here, well, if I have a uniform distribution, if I have n particles in the box, so n number of particles in box, then the proportion of particles that are in this range right here, well, would be the volume of this segment right here divided by the overall volume. So why don't we call this volume of